Do you want to share the screen to try and see if it works?
Oh, it's disabled.
Like part of the
Try it now. Okay, it's still disabled.
compartilhar. Okay. Okay, now it should work.
Okay. Yes. So you should setting it up, but okay. Do you see my slides in full screen?
Yes.
Okay, great.
Is it big enough? Just wait a few more minutes because some people are still arriving because we have to change rooms.
Okay, no problem. Yeah.
Going every time to one room, and today is an exception.
No problem.
Menor? Enche de guarda-roupa velho.
Que a hora é só para trabalhar, vocês não terão muito.
A gente não teve reunião essa semana, só fica. Agora vem mais cedo isso, mas. Não sei o Pois é, para fazer esse negócio aqui. E aí, nisso. E aí, todos os projetos paralelos também para ver se envolvem as coisas. E agora isso fica dando pequenas modificações também no trabalho dos usuários, né? Porque é da transmissão, né? Eles falam tudo isso.
I guess we can start.
Ainda não começou a falar.
What was that?
I guess we can start if it's okay with you.
Yeah.
Okay.
Quer dizer que o seminário para a Ana
Okay, so welcome everyone to today's seminar. Today we have Professor Ashley Villar. Ashley received her bachelor's in physics from MIT in 2014 and her PhD in astronomy in Harvard in 2020. She was formerly Simon's Junior Postdoc Fellow at Columbia University and a faculty member at Penn State before joining Harvard in 2023. Thank you very much, Ashley, for accepting our invitation. She'll be talking about time domain astrophysics in the era of big data. You may start when you're ready.
Okay, thank you so much. Thanks so much, guys, for having me remotely. If it's possible, I'm very happy to take questions throughout. I'm just having a slight hard time hearing, so like yell it into the computer if you have a question. So yeah, I'm very excited today to tell you a bit about my work that's in time domain astrophysics. We'll talk about what that means. And then this era of big data, we'll talk about what that means. And good. And I want to note that really this is a talk. It's kind of odd in that most of it's not science, it's methodologies, the methods behind science. And that's because I'll show you that this field of time domain astrophysics is really entering this new era of exceptionally large data sets. And so we really have to change the way that we're asking scientific questions to be able to to fully capitalize on the data available to us. So when I say time domain astrophysics, what do I actually mean? Time domain astrophysics is the very active evolution of the universe. So instead of talking about millions of years timescale, which is pretty young for the universe, we're talking literally days or hours, weeks. Human timescale changes in our night sky. And in particular, my group really thinks a lot about eruptions, collisions, and explosions of stars in our night sky. And we see these as basically bombs that will flash brighter than the galaxy that they went off in for a few weeks at a time. So because we're going to talk so much about data and methods, I really want a very clear picture of what it is we're talking about here. So we have these wonderful surveys now of the night sky that take new images every night. In the left-hand side, you can kind of see what they're looking for. This is a fake image, but you see that this like new star seems to appear and it gets brighter with time and then dimmer. So every night, we take these new images, we subtract them from each other to highlight only the new photons that we're receiving. And those photons represent typically the death of a star. And we call that death a supernova. That supernova, a number of high energy physics can be causing the light that we see. And so what we want to do is to use that light to untangle that physics. So if I really wanted to do this, what I would hope to accomplish is to take a multi-wavelength image or spectrum at every single moment of time. So I really know what every photon being released from this explosion is doing. If I did that, if I did that, I would get the lower right GIF here. It's representing me taking a series of spectra over time. And from this, you can really extract a ton of physics. The overall bulk properties, so like the overall shape that's evolving, is typically a black body, and it's telling you all about the bulk kinematics of that explosion. And then these little wiggles on top are a combination of absorption and emission lines from either elements that are sitting on the outer layers of a star as it exploded, or are actually synthesized during this explosion. Okay, unfortunately, making this GIF with real data would be really expensive. It's very expensive to take spectrum. These things are so dim in the night sky now that it easily takes half an hour to get just one snapshot in time of the spectrum. And so we have to work with a much cheaper version of this data. What we do instead is we take big buckets of photons. So we ask, like, what are all these blue photons doing versus all the red photons? And we can show plots of that as a function in time. And that's what this upper right-hand curve is showing. This is called a light curve, and we'll work with these a lot. So I'm taking photometry over time and looking at the light curve. And this is a low resolution version to the physics that are happening here. So our goal is to kind of disentangle, still tell that story of the physics, how the star died, but with this kind of poor man's data. So I want to quickly argue that it's easier than you think, though, to extract physics from even not the best data. And that's because the range of physics that we're looking at is exceptionally wide. And so here I'm imagining that I have something like a light curve, and I don't even have many points on that light curve, but I can measure things like how bright did this thing actually get at its peak brightness, and how long did it last for? And in a cartoon version, I'm showing here a few different transients, transient events that we can see in the night sky that live in this space. And so we can do things like say, oh, if something lasts for a few years and doesn't get very bright, well, it's probably just an outburst from a massive star or something. On the other hand, if it's still not quite bright, but it's happening on a day to a week time scale, well, there's a chance that that is the collision of two neutron stars. So even just these like simple properties really highlight the physics. This is quantitatively true as well. So here I'm showing you the same, I'm going to start calling, Sure. I'm going to start calling this a phase space. So the same phase space, duration versus a luminosity. But here I'm showing you contours from a theoretical study that really was asking the question, hey, if I want to power a supernova by the radioactive decay of nickel-56, let me vary every which way I can, different masses of the progenitor, the energy of that explosion. What is the contour of possibilities of that theory? And it really is the case that, well, one, there is a pileup. There's some places where it's really hard in this phase space to tell the difference between this physics, but there's some places where it's really easy. If something's really, really bright and it lasts for a very short amount of time, this has to be a relativistic type of event, like a jet, which produces gamma ray emission. Okay, so this is all to say that the ultimate goal of the work we're doing is to connect the zoo of observed variability in the night sky to the underlying high energy astrophysics. And this data that we get is not going to come labeled for us. All of this is popping off in the sky all at once, and it's our job to disentangle and to tell the story of stellar evolution through the sum of all of these explosions. Okay, so traditionally, let me just very quickly tell you how we do that. Traditionally, we classify supernovae, the deaths of stars, through a spectrum. So in that GIF, I took one snapshot that took like half an hour of a very big telescope of time. And I look for those spectral lines that we saw. And I ask just simple questions like, oh, do I see hydrogen in emission or absorption in the spectrum? And if yes, well, then I know that that must be some type of star that had a hydrogen envelope. So it must be something like a red supergiant that exploded. If I don't, then it means that it's something that in one way or another lost its hydrogen envelope. And so a great example of this is if a white dwarf explodes as a thermonuclear explosion, I don't expect to see hydrogen or helium. Okay, and then I can go a little bit deeper and ask questions like, well, sorry, I'll say it a different way. As we started to find more and more transients, we realized that, okay, it's not always this easy. Sometimes we see hydrogen for a little bit, it goes away or it shows up. And so someone say, okay, there's some like in between where maybe I'm type 2, but type 1-ish. And as we've been increasingly seeing more and more transients, this zoo has really gotten a little complicated, where we now have a pretty wide variety of astrophysics, even just in exploding stars that we can find in the night sky. And our goal still, though, is to take these kind of snapshots of possible death and connect it into some coherent picture of, so the one I care about is how massive stars are dying. Okay, so here's, oops, I'm so sorry. Here's a problem. Transients are traditionally classified via their spectra, but I told you that that's very expensive. And so we are not going to use spectra anymore to classify the underlying physics. We have to work with light curves. Luckily, these things are entangled. If I have a hydrogen envelope, how do I want to say this? The recombination of hydrogen actually impacts the explosion we see. And so we can still infer that from the light curve, this kind of poor man's data. And we don't require getting a spectrum. But it is often very difficult to get. Have I moved? That was weird. It is often very difficult to extract that physics. But that's what we're after. We're going to turn this traditional classification method into something new that can work with the cheaper data product. And in particular, I just want to note that a lot of the data, the light curves that I'll show, come from this survey that I'm a part of, the Young Supernova Experiment. That works with the Pan-STARRS Observatory in Hawaii and observes about 1,500 square degrees of the night sky almost every night if the weather isn't bad. And our goal, like it sounds like, is to find young supernovae, catch them early, and to really get after what did the progenitor star look like on its kind of last day of life. I also want to highlight that we have a new data release from this year that contains 2,000 supernovae, and we'll talk a bit about how we go about classifying these into different types. Okay, let me tell you though the numbers game. So I'm telling you, okay, we observe all these explosions every night, but how many are we actually looking at here? It's a lot more than you might think. I'm showing here a plot of number of supernovae discovered as a function in year. There's a few things I want to note. One is that there's a log scale on the y-axis. So the discovery rate of supernovae has been exponentially growing for the last few decades. In the 80s, we would find a few dozen per year. And nowadays, we find about 20,000 per year, supernova candidates. That's what the light blue line is showing you. The dark line is showing you what fraction of those actually got a spectrum or the traditional classification label attached to it. So that type 1, type 2 label. That's also growing exponentially, which is great, but unfortunately, it's definitely lagging behind the number of discoveries. So right now, we only get spectra for a traditional label for about 5% of this data. And I am not exaggerating when I say that the field as a whole basically throws away the remaining 95% of the data. We just don't do anything with it. Okay, fine. I mean, maybe you're not fine with this, but the field's fine with this for now. But in just a few years, oh, it's out of date. I keep forgetting to change it. In a few years, the Vera Rubin Observatory, whose namesake is in the bottom right corner, will be coming online in Chile, and will start observing the southern sky every few nights for a decade. And what's so exciting about Vera Rubin is that it's going to be a really unprecedented depth at the cadence it's at. So it's really observing the universe. It's probing deeper into the universe than we've been able to do before on an area of the sky way larger than what we've been able to do before. And so we can take that graph that we just saw of the discovery rate over time, and we can add Vera Rubin to it and see that it's drastically going to change the landscape of supernovae and time domain astrophysics as we know it. So I'll let it keep. Okay, I think it has no, it's still going. Okay, well, we're going to stop it. So I had that on this linear scale, so it was a little dramatic, but it really is this dramatic change in the field. So Vera Rubin is going to break the exponential growth that we've been experiencing, and it's going to increase our discovery rate of supernovae by 2 orders of magnitude to over 1 million supernova candidates every single year. We are not going to get a Vera Rubin of spectroscopy. That's not really. There are really wonderful spectroscopic surveys coming online, but the number of spectra we get for supernovae isn't going to grow by more than a factor of 2 or something. It's basically constant. So that just means that now the fraction of events that we get a traditional label for, so the ones we actually do science with, is going to go down from 5-ish% to something like 0.1% of all supernovae. And so the field is at a crossroads where we can decide to do something with the 99.9% of events that have no spectroscopy, or continue what we're doing and only use 0.1% of the data. Obviously, I think we should do the former. I also want to say that this creates more than one problem. So not only do we have this issue that very few events get a spectrum, we also have this really exciting opportunity that if we're discovering 1 million supernovae every year, realistically, we can actually start being sensitive to 1 in a million level astrophysics. And there's a question of, one, what does that even mean? What does it mean to be 1 in a million? Does it mean intrinsic rarity? Does it mean something we haven't seen before? We don't know. But we want to be able to actively tag these exceptionally rare sources in real time, and we only really have one chance to do so. Okay. What's exciting about that is that 1 in a million is really like probing. How do I want to say it? Even the most rare phenomena that we know of now will be ridiculously commonplace in LSST. A good example I like to talk about are these like super luminous supernovae. The name suggests what they look like. They're very bright for how long they last. We think that's because they birth what's called a magnetar, a really highly magnetized neutron star that as it spins down, it provides some additional, it transfers its angular momentum into kinetic energy of its ejecta. And so there's like more oomph in the explosion. The key point is that this is less than 1% of the intrinsic volumetric rate of supernovae that we know about. Exceptionally rare, although lots of efforts have increased the statistical samples of these things. But with LSST, we'll get like 10,000 per year of these things. These are in no way those exciting needles. They're very much in the haystack of things. And so really, we should be expecting unknown, unseen physics in LSST. And we need to be prepared to somehow be sensitive to that. Okay, so I'm now going to just chat about methods that we are preparing to tackle exactly these issues. Specifically, I'm going to tell you how we're tackling the issue of classifying, so moving from spectroscopic classification to photometric with the light curves, identifying anomalous physics, and then analyzing the full set. I'm happy to stop for questions if there is an ability to do so.
Yes, if somebody, do you hear me?
Yes.
Yes. Does anybody want to ask questions now or wait till the end of the talk? They want to wait till the end.
That's fine. Okay, that's good to know. Great. Okay. So we've set up the problem. Let's set up some method solutions. Let me be super clear about these 3 words. So let's pretend I see lots of new supernovae in the night sky. I'm representing them as stars in this new phase space. One is the mass of the progenitor star, and one is the energy of the explosion. And I just want to ask questions, or let me say a different way. When I say classify, I mean that when I see this new gold star, maybe it looks very similar to these blue stars in this energy mass phase space. And so I'm trying to classify in a probabilistic way the gold star as a member of the blue class. If I see this new gold star, I see that it looks really different than the blue ones I've seen before, really different than the red ones I've seen before. So I'm attempting to identify novel physics here, the needles that I should be following in real time. But then finally, to even make this sort of phase space where I like magically know the progenitor mass and I somehow know the energy, well, I need to do some physics to get those numbers to begin with. And that's what I mean by analyze. And this is hard when we have a million events every year. Okay, so the way we're going to tackle classification is to extract features from the light curves so that we can classify them into known classes, just like we did here. One of the issues is that I told you there's like a zoo of physics. So there isn't one magical physical model to rule them all. Instead, one thing that we've tried is to fit empirical parametric models. So design an analytical function that looks kind of like most supernova explosions. Here I'm showing you that function that has really interpretable features. Like I can tune what the amplitude is, A. I can tune the explosion time, T naught. I can tune how fast it rises, tau rise. And even though these aren't directly related to the physics, this can at least pull out some descriptive features so I can start making those kind of phase spaces and those scatter plots to start the classification task. This works pretty well. We have done this now, I'll tell you, for quite a few samples. And what's nice about this is we can like fall back on statistics that we know really well to understand how uncertain we are about this. If I have lots of points, I can constrain these light curves. That's why I'm showing you here quite well. And if I don't have so many observations, well, then I have some uncertainty in my constraints. And that's going to translate into an uncertainty in the classification. There's still an issue. These aren't physical. And so I don't really know exactly how I should combine these features, like the rise time, the amplitude, into a probability. Like, what combination of these means probability of type 1a versus a probability of a type 2? Well, I don't know. And so what we've chosen to do is to use neural networks to try to solve this problem for us, because we don't have a physical description of how these equations should look. The reason why we've gone with neural networks is because they're very good at the task at hand, in that they're very good at coming up with nonlinear combinations of features to predict some function. Nonlinear meaning that I don't just have pluses and minuses, I can have multiplications and divisions. And the function meaning like, what is the probability of type 1a? I will not, for the sake of time, do my little short description, but like in Q&A, I'm very happy to talk through how this neural net works. It's really not so hard. The key thing just to know is like that it is a nonlinear it learns a nonlinear combination of my features to predict whatever I want, like a probability function. Oops, okay. Sorry, my mouse loves to skip. So using these neural nets, we have been able to successfully classify supernovae into their traditional spectroscopic types, type 1, type 2, but using the light curves alone. And we can do it pretty well, actually. Here I'm showing a result my students writing up on the a survey of supernovae called the Zwicky Transient Facility, where she's been classifying thousands of supernovae into their traditional labels and doing a pretty great job. And if you want to see these classifications yourself for in real time, basically, this is actively running on what's called a broker, so like a website called the Antares broker, and provides classification for supernovae every night. And in fact, like, this is becoming a common task. We've applied these same methods to a number of surveys. The Pan-STARRS Medium Deep Survey, also conducted on Pan-STARRS, the Zwicky Transient Facility, that's the work I just highlighted, and also the Young Supernova Experiment, that survey I highlighted previously that we just had data release for. So those data release classifications use these sort of methods to tell you what type of supernova we think that we saw. How am I doing on time? I'll try to go faster. So we can also classify with 0 photons, which sounds kind of wild, but we don't actually need supernova photons to get a guess at the underlying physics. And I'll explain why that is. It's because the supernovae understand where they come from, as in, that's a fancy way of saying there's correlations between the galaxy type that has hosted a supernova and the supernova type. Why is that? It's related to just the underlying physics. If I'm a massive star and I explode, I probably am, well, okay, I'm massive, so I know that I die really young. And so I'm probably in a galaxy that is actively undergoing star formation, something like a spiral galaxy. If I'm a thermonuclear explosion, which just means a type 1a or a explosion of a white dwarf, that's all the same thing. Well, my white dwarf is pretty old actually, so it took a long time to make that. These can happen wherever. So if I see something in a red and dead galaxy, it's probably not a massive star exploding. It's probably a type 1a supernova. And then this is even true for really rare types. I'm going to bring up this weirdo, the superluminous supernovae guys again, which remember those magnetar guys. They also have weird preferences we don't even understand. They love to happen in low metallicity galaxies. Maybe this has something to do with mass loss, which we know should be weaker for these low metallicity environments. Not really sure. But the key point is that even without seeing the supernova, this context of where it was living tells us something about the explosion. And in fact, using very similar methodologies, using neural nets again, and using images of the host galaxies, we can subdivide at least into thermonuclear or type 1A explosions versus massive star core collapse pretty well. So I'm showing you, and I showed this before without quite explaining it, a confusion matrix of the true underlying label. Is it really a type 1A or a core collapse? And what our neural net predicts. The way you should read these is if it's a dark diagonal, that's good. It means that they agree with each other. Okay. Do I want to talk about this? I will talk about this, sure. Well, okay, I'm actually going to skip this if you don't mind for the sake of time. This is a different new work where we've been thinking a lot about these host galaxies and how to extract interesting parameters of them. I'm just going to skip it so it's easy. One thing that's been cool though is that we can make lots of fake galaxies and tune their physical parameters. And so we're using this to help us classify supernovae. Let's skip ahead though to the second task at hand, the identification of interesting needles in the haystack in real time. If we use the method I just described, fitting a model, using the features to classify, that doesn't really work here. The reason why is because when I only have a few points, I'm actually really uncertain of what this thing's going to do in the future. And so is there a way instead for us to pull out features that can change in time and be a little bit more certain? To do that, we're going to go back to deep learning methods, neural nets, but we're going to use a really fancy type of neural net this time. And in particular, this is an unsupervised variational recurrent autoencoder. And we're going to talk about these words because I want to emphasize they're chosen because they all kind of serve to a different purpose that's very specific to the problem at hand. So unsupervised in particular, we only label, what do I want to say? We want to design a method that is sensitive to new physics. So I need to be able to train such a method without really telling it the physics it should be looking for. Unsupervised means this. It means I'm not labeling anything. I'm just saying, hey, here's a lot of light curves of supernovae. Can you figure out in general what these should be looking like? And then we're going to use that to our advantage. We make special neural networks that look something like this. And this is really similar to the neural net I showed you before, where remember the input was like features of the light curve and the output was a probability. The only difference here is that the input and output is going to be different. The input is going to be a light curve. Different filters, photometry and different filters as a function in time. The output is going to be the exact same thing. So I'm asking this neural net to just photocopy a light curve for me. Trick though, is that I'm going to tell it, during this photocopy process, I need you to condense that data down. You're going to have a little bottleneck where all of the information within this light curve needs to be squeezed into a small vector. So even if this is like 100 points of photometry, I'm only going to give you, as an example, 10 points to make a scatter plot phase space to plot this in. And in doing that, we learn this encoded representation of the light curve. So the way you should think about this is just like before. I showed you a scatter plot where it was mass versus energy. Imagine essentially that the first element of this space is something like mass, and then the second something like energy. And then in the physical representation, if I have mass and energy and I know the physical equation, I can write down the equation, plug in those two numbers, and reproduce the full light curve. That's what's happening here. If I know these 10 numbers, and then I know some other twists and turns of the nonlinear combinations, I can turn it into a full light curve. So that's what we're attempting to do here. To be super, super clear, this is not physical. Whatever it's learning is not physical. It's just learning a representation of the light curve, and we're going to use that to our advantage. So that architecture, me inputting something, outputting the same thing, and squishing it in the middle, that's called an autoencoder. Variational just means that, I actually have like uncertainties on these observations. I measure uncertainties. I would like to also have uncertainties on these learned parameters. Like I would normally have an uncertainty on mass, an uncertainty on energy. Can you do that for me? That's what variational does. It produces not just the representation, but also some idea of what the uncertainty of that representation is. And then the last little buzzword was this idea of recurrent neurons, a recurrent neural network. The idea here is that I want to be able to update what it thinks my representation of a supernova is with better and better data, because I have data actively coming in every night. And so when the data first arrives, I have some encoding. And as I receive more data, that encoding in theory gets to be better and better. Okay, so if none of that made sense, I just like to show this little cartoon that I think makes a lot more sense. So this is this autoencoder, or variational autoencoder, VAE, happening in action. This is a real light curve. It's a type 1a, and I know that because we got a spectrum for this one. The real data points are the dots. And the error bar is shown as this error bar. So, oh gosh, sorry. So we only really have like one high signal to noise point, and everything else is kind of bad. And to be clear, this is in 4 different filters, GRIZ. The lines are showing you the output of my neural net, what it thinks the supernova will look like during this and forecasting in the future. So it's using the representation it's learned to build a model of the supernova and then telling me what it thinks it should look like. When I only have one data point, it does a terrible job. Like, this is not good. This is really dim for type 1a. It has like a weird duration, just not good. But a few days later, I get a few more points, and the neural net kind of picks up on the fact that this looks a little bit like a type 1a. It now reaches about the right magnitude. And if we wait until the end, we even get these kind of secondary characteristics of a type 1a in Z-band. This like secondary bump shows up. So by just showing our neural net lots and lots of examples of supernovae and not telling them about the physics, I'm just saying, look at all these supernovae. It has learned how to generally build up the light curve model for these events. So now what we can do is make the same like scatter plots. So take lots of supernovae, turn them all into these little representation vectors, and then look at the scatter plots. When I look at those scatter plots, I see something like this. So all of these points represent the representation of a supernova. And I can do things like say, oh, hey, most of my supernovae are clustering here in this space, but I see some weirdos that really don't want to cluster. And what's exciting is that we can call these weirdos anomalies, the needles in the haystack that maybe we want to follow up in real time. And in fact, we did this study with a big simulated set of LSST-like light curves, where we just asked the question, like, what are you calling weird using this phase space that we've made? And do they actually correspond to rare physics? And because we've tagged all of the physics in the simulation, we know exactly which one is rare and which one is not rare. And so in this case, I'm showing you an example of a superluminous supernova, which in the simulation is like one of the rarest things we could put in, because we don't really know anything rarer than this right now. And then I'm showing you, where do we want to go? As a function in time relative to peak brightness. So this is peak brightness. This is the full light curve. This is peak brightness. At what point does my light curve in this phase space I've learned look weird enough that it's in the top, I forget the number, but like 1% or 0.1% of weirdness. And the way we think about that is we make this scatter plot, and I watch the representation of this supernova travel in time. So in this plot, the opacity of the point represents time. So it starts kind of in the mix of the scatter, and you can kind of see it walks away from the distribution. And as it does that, that's how its weirdness score increases and how we're able to say, oh, this is actually a really weird supernova. And so it's great. We were able to show that using this method without inputting physics, we can be sensitive to really rare physics without having to know what it looks like. We just need it to look different than everything else. Great. Okay. So we have classified known physics. We have figured out a way to identify rare physics, even without knowing what we're looking for. The last step is to do physics. So we need to now actually analyze these events. And by that, I mean the traditional thing. We need to write down, how do I want to say it? If I know this is a core collapse supernova, I need to be able to write down the equation of that supernova, figure out, hey, what was the progenitor mass of that explosion? What was the kinetic energy? The issue is that that's a really expensive task, actually. And let me explain why that's expensive. The way we would normally do this is I would write down my physical model, and then I would plug in some parameters. And so I'd say, okay, if my mass was 10 solar masses, my energy was 10 to 51 ergs, I think this is what the light curve should look like. I compare that model to my data. I see how well it matches. And then I go back to the drawing board, I change my parameters, and I try again. And so I'm just describing here any sort of statistical inference method. So people might be familiar with Markov chain Monte Carlos or nested sampling. And this dance of going back and forth, trying something new, checking my answer, trying something new, checking my answer, can be really expensive. And so what we are, what do I want to say? When we get to the era of seeing 1 million supernovae per year with current methods, this can easily start costing us millions of CPU hours. That becomes prohibitively expensive to fit all of these different light curves to their physical models. And so the last thing that we've been attempting to do is to once again speed up this process, again, using machine learning and neural networks. So I'm very much cartoonifying this. I'm happy to talk about this in detail if people want during questions, but I want time for questions. We're using a special type of neural net that I'm not describing well right now, to basically look at lots of simulations of supernovae again, look at their light curves. And this time I'm tagging all of them with the underlying parameters. So in this example, I'm saying, okay, here's the mass, the ejecta mass of all of these supernovae. And here's what their light curves look like. I train a probabilistic neural net to essentially learn the joint probability between all of the observables, so the light curve, and the parameters that I tag the light curve with. Then what happens is that in test time, I can show this trained neural net new light curves, and it conditions on those parameters in one go. And so I can kind of bypass statistics really, really quickly by just showing a neural net in advance lots of examples of what it should be doing. And in particular, sorry, there's a little bit of jargon in this. In particular, so in test time, meaning when I get a new supernova, I show it the data. Oh, it doesn't know. It should not know the mass. But the point is that it gets out full posteriors. And it gets out these posteriors without any assumption on their shape, so I don't have to assume Gaussianity. And they're pretty well calibrated, and we can talk about what that means. But what's exciting about this, so we just did this last year on, again, just a simulated data set. But what we showed is using this method, one, you get pretty realistic posteriors out, meaning fits out. So here I'm showing you the most cartoon version of this. This is my data. We've passed it through this neural net. These lines are showing you the best fit model. And like by eye, they look pretty good. If you go to the paper, we show that they are pretty good statistically. So importantly, instead of taking normally hours to fit a supernova, which is what it would take, it takes about 10 milliseconds per supernova. And that means that if I like scale up to LSST, so 10 years of 1 million supernovae every year, so that's about 10 million, I can actually fit all of them in one go on my laptop in a day. So suddenly this goes from computationally prohibitive to like incredibly cheap. And so we've been thinking a lot about how to use these types of methods to really understand that haystack, the 99.9% of supernovae, which we don't get a spectrum for, which we don't follow up in detail, and using them to constrain populations of core collapse supernovae. Okay, so I'm going to leave up my conclusion slide, and I very much would like to take time for questions. So thanks.
Thank you, Ashley.
Thanks.
We're open for questions, starting with Kepler and then the students. Okay, starting with my student. So if you want to talk loudly or come closer.
Ashley, do you hear me?
I hear you. Is someone else talking?
There's only one.
Hi, Ashley.
Hello.
Nice talk. I'm wondering what kind of methods do you use to deal with the misclassifications of your neural net?
Yeah, that's a good question. We don't really do anything. So we try to understand how we are misclassifying. So how do I want to say it? If I go all the way back, this might be helpful. Blah, 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 blah. Wait, did I pass it? I definitely, so sorry. Okay, so here's my confusion matrix I showed. And so you can see, for example, the types don't really matter, but I seem to confuse type 2Ns a lot with superluminous. Okay, so I don't try to correct that, but I just try to understand that bias. Now I at least know, hey, of my sample of the things I call type 2N, 17% are probably superluminous, 15% are probably type 2, etc. And what we do is we build that back into, we haven't done it yet, but what we are aiming to do is to build that back into statistical models. So as long as we understand how we're wrong, we won't be correct. We can't be certain we're correct for any one supernova, but for the collective population, we understand our bias. Does that make sense?
Yeah, so do you think that you need different methods for leading to different misclassifications?
Yeah, totally. So we have worked with we've worked out methods to compare. We create what are called agreement matrices, where we actually write down how much we think we should be agreeing, and we check to see if it matches expectations.
Yeah. Thank you.
Kepler?
So actually, in the model light curve, you presented absolute magnitude. So you must know the distance.
Yeah.
In the data, you don't. So
Yeah.
do you normalize for the pre-supernova points or what?
Yeah, that's a really good question. And in this, we assume that we know redshift. And we knew that in this, okay, what do I want to say? In this, we assume we know redshift. I agree with you. I think that's a bad assumption. So most of the time we don't. We know a photometric redshift of the galaxy, and those are really bad. In the newest method that my students are preparing, we don't actually rely on redshift anymore.
But you probably then need the pre-supernova measurement to normalize by that.
Yes, that is what we do. We use, well, we don't even, what do I want to say? We don't even normalize. We just stay in flux space now. Yeah.
Do we have more questions about the methodology? Okay, so I might have one. So you skipped some parts that you were gonna
Oh, yeah.
the outing code. No, I think
Yeah.
optimization.
I'm happy to talk about this. It's cool. It's just like kind of different. A project we just did that was just accepted with a really awesome postdoc, Alex Gagliano here. So we wanted to know, what do I want to say? We know supernovae are fundamentally, they know about their galaxy, star formation rate being one of the big ones. Like they know whether or not you're star forming because massive stars are in star forming regions. Okay. The issue is that when we look at a galaxy, we don't know if it's star forming or not. Like we just know the colors of the galaxy. And so what we aim to do is to try to make actually an autoencoder, even though I didn't call it this yet, to predict the properties of that galaxy. And in particular, we told our autoencoder, you need to optimize 3 different things. One, I'm only gonna talk about 2 of them. One is to, using a separate method, we have some estimates that was very expensive for the parameters of these galaxies, the mass, the redshift, the star formation history or rate. Second, though, I also want you to be able to recreate the image of the galaxy. So why would I want to do that? Because the morphology of the galaxy also does contain information. Star-forming galaxies have grand spirals in them. And it's hard to quantify this notion of like grand spiraliness. So there's some idea of morphology that we can't quite quantify. And so we're going to do that by telling the neural net, hey, do your best to just remake the picture. And then we also just make sure that the space, that part doesn't matter. We do one more thing, doesn't matter. Okay, so we've trained a neural net to do this. And what we can do is one, now use it to predict the different properties of galaxies based on their images alone. So here I'm showing you photometric redshift estimates here, inferred masses. So on all of these, y-axis is our neural net, x-axis is our ground truth, which all have uncertainties on them. Star formation rate is really hard to measure, but like we do pretty good job given how uncertain they are. And then this is the just the angle of the galaxy. But then what's cool is we can say, oh, now I can like play with that neural net and ask it things like, hey, what do you think rotation angle makes an image of a galaxy do? And so I'm showing you here the same properties of a galaxy, but only changing what neural net thinks rotation angle means. And you can see it does seem to rotate the galaxy. Same with redshift. Again, everything's held fixed, except I'm changing the redshift. And it seems to do something kind of reasonable. It goes from like a white blob to a dim little red blob you can barely see. Star formation rate changes it from like a yellowy blob to a bluer blob. So this also seems to be doing something, right? And then this kind of, oopsie, ambiguous last part is this like idea of morphology. Sorry, my mouse does not want this to show up. Where here, as we vary it, it's kind of hard to explain what's happening, but it does seem to be getting more edge on, I guess I'll call it spiral, over changing this parameter. So anyways, we've been using this so we want to use this to help us classify supernovae. We've just kind of been using it for a number of fun tasks. One is to find anomalous types of galaxies in images. So we can do things like ask, hey, I know this is a green pea galaxy. Those are these low mass, high star formation rate galaxies. Can you find me the nearest neighbor in that phase space you've made to find me more green peas? And these do look like green peas. And similarly, there are these things called red spiral galaxies, which appear to have spiral arms, but have low star formation rates. So they're very red. And this has done something similar where it's finding galaxies that also appear to be low star formation rates, but have spiral arms. So that is what I skipped, but it's just kind of a fun, yeah.
So we have a question from YouTube that is from Chico Jablonski. He asks, says, thank you for your talk. And he asks, Is this not more a pattern recognition than a time domain approach?
I'm so sorry, can you repeat that?
So he asks, is this not more a pattern recognition than a time domain approach? I'm not sure about what part of the talk he was asking, because maybe it was before.
No, totally. Yeah. For like the light curve stuff, blah, 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 blah. I mean, kind of all of it. I agree with that statement. Totally. Like all I'm doing is I'm showing a neural net lots of examples of something and saying, please find me, or please figure out how to build up these shapes. There's no physics in this. This is just pattern recognition. But the power in that is that the physics is so diverse that I can't write down a physical model. I kind of have to rely on pattern recognition. And that's why neural nets are such a great solution to this problem.
Oh, do we have any more questions from Zoom? Okay, we have one here. Can you control?
One question.
Come
You
closer.
can hear
Then.
me?
It's better to come closer.
Okay. Hi, Ashley.
Hey.
Regarding to the real-time detections,
Yeah.
you have the possibility to share this information with, for example, Gravitational Wave Observatory, or to do multi-messenger astronomy?
Yeah, that's a really good question. We have not done this, and what do I want to say? We haven't done we haven't done this yet. Part of that is because Vera Rubin Observatory just hasn't announced how it's going to do target. What do I want to say? Okay. Vera Rubin Observatory is not very well tuned in its survey cadence to find gravitational wave counterparts or kilonovae in real time. And so the way it should do this is it should use what's called target of opportunity mode, where it pauses its survey and it quickly tiles over probability regions from the gravitational wave detectors like LIGO. LSST has not yet, Vera Rubin Observatory has not yet announced that it's going to do this, so we haven't done this yet. But I think that would be great use of it.
Do we have any more questions? Or if not, let's thank Ashley again. Thanks a lot.
Thank you.
Bye.
No, espera, tú vas a